Vector resolution is the fact that any vector can be represented as the sum of two perpendicular vectors. Suppose we have a vector that looks something like this, r, and we're told that this vector to the horizon is on an angle of theta equal to 37 degrees. It's important to note that based on our geometry rules, we know that we can draw this as a triangle that represents two perpendicular component factors, two component vectors. It's useful at this early stage of the game to match it up to our standard axes, which would be, of course, our horizontal and vertical axis as a frame of reference here, where we would call this the positive x direction and we would call this the positive y direction. Now, of course, we can alter that frame of reference once we get familiar with the concept, but for now, let's just go with that. So if we look at this vector and we say that r is pointed in the positive x direction and the positive y direction, right, it makes sense that we can trace out a component vector that points solely in the horizontal direction that then combines with a vertical vector that points solely in the y direction. And so we label here the horizontal as rx as a vector, and of course this one would be r sub y as a vector. And so the vector statement would be that r sub x plus r sub y is equal to r. Now keep in mind that these are vectors, and so it's not a direct sum of this side plus that side equals that side. Instead, it is Pythagorean theorem, rx squared plus ry squared equals r squared in terms of magnitude. And then, of course, the direction, the plus or minus, is dependent on our frame of reference over here, and that will be used once you separate into the x and y directions. What we're going to be looking at is projectiles in two dimensions where motion is originally given as a total sum vector, but then must be divided into horizontal and vertical components in order to be assessed and analyzed further on through the problem. So in vector notation, we have this sum indicating that it's a Pythagorean theorem triangle where these two things are perpendicular. In terms of the magnitudes, we know that rx squared plus ry squared equals r squared in terms of the triangle magnitudes. We also know that based on the angle theta, using the general form, we can say that rx is equal to the magnitude of r times the cosine of theta, and that ry is equal to the magnitude of r times the sine of theta. Now again, these are magnitude formulas that are simply allowing us to find the lengths of the sides of the triangles, and then we're using our frame of reference to decide whether or not this is positive and this is positive. And of course, it all stems from a technique that is being intrinsically demonstrated here, and that's called head-to-tail addition. We will incorrectly assess the directions of rx and ry if we do not draw our diagram head to tail. Head to tail meaning that no matter how I want to demonstrate the sum that indicates r, when I draw my first vector, I start where the beginning is, right? We're keeping in mind that vectors could potentially be a displacement, so we think of this as from start to finish. And so in terms of drawing in the components, if we start at the starting point and we draw the first component, and then without moving our pen, although I am going to switch colors, without moving from that position, right? So we drew our first vector up, and then from going up, we drew to the right. And so the statement should be the same regardless. To the right and up yields r, or up and to the right yields r, right? And so in both cases, the vectors are perpendicular, and of course this vector over here would be equivalent to this vector over here, ry, and this vector down here would be equivalent to this one up here, rx. Keep in mind both triangles follow the exact same rules. By alternate interior, based on the parallelogram that we have, we know that this angle would then be theta as well. And if you trace through, ry is r sine theta and rx is r cosine theta. And so they're both correct as long as you've drawn head to tail, right? Do not be tempted to just draw the sides of the triangle mindlessly, because it's very possible, if you were given an r that pointed like this, where the angle is known down here perhaps, from here to there is theta in this particular diagram, right? Don't be tempted to just willy-nilly draw the sides of the triangle in, because we have to make sure that the vectors that you indicate as the sum of this yield the same directions that you would say if you were to say out loud to yourself, this arrow points down and to the left. And so my horizontal component is to the left, and my vertical component is down. Drawing those things head to tail, I drew the first vector, then I drew the second vector, right? And then I said to myself, this is to the left and down, r is to the left and down, and so that's appropriate. And so then I would label this as rx, and I would label this as ry, and then I would go through my triangle in order to determine where theta lands. In this particular diagram, based on the way I've drawn it, theta would have an alternate interior on this side. And so in this particular case, we know that we see that rx is actually equal to r times the sine of theta, and ry is equal to r times the cosine of theta. And again, these formulas are just dependent on the orientation of the triangle and which angle is being represented. The actual directions, here being positive in the x and y direction and here being negative in the x and y direction, are dependent on how you draw the triangle and would be assessed after you've solved this value, right? So once I know that this is a number, then I go ahead and put the sign in as plus or minus before I continue on with the remainder of the problem. This will be very obvious as we practice more and more with the two-dimensional projectiles in maintaining proper direction for where the objects move as they fly through the air.